I'm Dr. N. Vasumathi, Professor of Mathematics, Siddhartha Institute of Science and Technology. In this video, we discuss about the Bernoulli's differential equation and exact differential equations, and we'll find the solution of both equations. First of all, we discuss what is Bernoulli's equation. An equation of the form dy by dx plus py is equal to qy power n is called a Bernoulli's equation. Here p and q are functions of x only. To solve this type of equation, dividing on both sides by y power minus n, we get y power minus n dy by dx plus p into y power 1 minus n is equal to q. By substituting z is equal to y power 1 minus n in this above equation, we get dz by dx is equal to 1 minus n into y power minus n dy by dx. Now, multiplying the equation 1 on both sides by 1 minus n, we get 1 minus n of y power minus n dy by dx plus p into y power 1 minus n is equal to 1 minus n times of q, which again is reduced by using the equation 2, a linear differential equation of order 1, namely dz by dx plus p1z is equal to q1, and this already equation is known as a Leibniz linear equation, and this equation can be solved by using integrating factor method. Now we discuss about exact differential equations. Consider the equation of the form p of x by dx plus q of x by dy is equal to 0. This equation is said to be an exact differential equation if we express the left hand side of this equation, namely p of x by dx plus q of x by dy is equal to the differential of some function, say phi, that is d phi is equal to p of x by dx plus q of x by dy. Since the right hand side of the equation 1 is 0, we get phi of xy is a constant function, and which is the solution of the equation 1. Also, d phi is equal to dou phi by dou x into dx plus dou phi by dou y into dy by definition of a partial derivative. We get p of xy dx plus q of xy dy is equal to dou phi by dou x into dx plus dou phi by dou y into dy, which implies dou phi by dou x is same as p of xy and dou phi by dou y is equal to q of xy. Now, the necessary and sufficient condition for the equation 1 to be exact is that the second order partial derivatives of phi are independent of the order of their differential. That is, dou square phi by dou y dou x is equal to dou square phi by dou x dou y. If such a function phi of xy exists, then the solution of the equation 1 is phi of xy is equal to constant. Now we discuss some examples of testing the exactness of the differential equation. For this, we consider the differential equation 3x square plus 4xy dx plus 2x square y plus 2y dy is equal to 0. This equation is an exact differential equation because the left hand side can be expressed as a perfect differential of the sum function f of xy is equal to x cube plus 2x square y plus y square. That is, dou f by dou x is equal to 3x square plus 4xy, which is named as m of xy, and dou f by dou y is equal to 2x square plus 2y, which is named as n of xy. Now df is equal to m dx plus n dy. The equation 1 can be written as a perfect differential of the function f, that is df is equal to 0, and hence by integrating this df equal to 0, we will get a solution as f of xy is equal to constant. Now in this we can observe that the second order partial derivatives dou square f by dou y dou x is equal to dou square f by dou x dou y. A differential equation of the form m of xy dx plus n of xy dy equal to 0 can be made exact if it satisfies the condition dou m by dou y is equal to dou n by dou x. Now, solve the differential equation 3x square plus 4xy dx plus 2x square plus 2y of dy is equal to 0. Comparing this equation with the m of xy dx plus n of xy dy equal to 0, we have m of xy is equal to 3x square plus 4xy and n of xy is equal to 2x square plus 2y, and dou m by dou y is equal to 4x and dou n by dou x is equal to 4x. Since both are same, we say that the given differential equation is an exact differential equation. Now comparing the differential equation with the df is equal to dou f by dou x into dx plus dou f by dou y into dy is equal to 0, we have dou f by dou x is equal to m of xy is equal to 3x square plus 4xy and dou f by dou y is equal to n of xy is equal to 2x square plus 2y. Integrating dou f by dou x is equal to m of xy with respect to x, we get f of xy is equal to m of xy dx plus k of y. That is, k of y is a function of y because we are integrating with respect to x. So which gives now f of xy is equal to x cube plus 2x square y plus ky. Differentiating this with respect to y, we'll get dou f by dou y is equal to 2x square plus dy dy of ky. Now from equations 3 and 5, we have 2x square plus dk by dy is equal to 2x square plus 2y, or dk by dy is equal to 2y. Now integrating, you will get k of y is equal to y square plus c naught, where c naught is an arbitrary constant. Now the equation 4 implies f of xy is equal to x cube plus 2x square y plus y square plus c naught. That is, f of xy is equal to c, which implies x cube plus 2x square y plus y square plus c naught is equal to c dash. If dou m by dou y is not equal to dou n by dou x, then the differential equation m of xy dx plus n of xy dy is not exact. We can reduce this non-exact equation into an exact equation by using the following rules. We can reduce the non-exact equations into an exact equation by using the following integrating factors. Under that, number 1 is m of xy dx plus n of xy dy equal to 0 is exact if dou m by dou y minus dou n by dou x whole divided by n is a function of x alone. Then an integrating factor for the equation 1 is mu of x is equal to e power integral of dou m by dou y minus dou n by dou x whole divided by n dx. And if dou n by dou x minus dou m by dou y whole divided by m is a function of y alone, then an integrating factor for the equation is mu of y is equal to e power integral of dou n by dou x minus dou m by dou y whole divided by m dy. Now we solve the differential equation y dx plus 3 plus 3x minus y of dy is equal to 0. This equation is non-exact equation because dou m by dou y is equal to 1 and dou n by dou x is equal to 3. Which equation can be made exact by taking the integrating factor as 1 by m of dou n by dou x minus dou m by dou y is equal to 2 by y, which is a function of y alone, and therefore the integrating factor is e power integral of g of y dy, or e power integral of 2 by y dy is equal to y square. That is, the integrating factor is g of y is equal to y square, which is a function of y alone. And therefore, multiplying the given differential equation with the integrating factor, we will get m of xy is equal to y cube and n of xy is equal to 3y square plus 3xy square minus y cube. And hence, dou m by dou y is 3y square and dou n by dou x is equal to 3y square. Both are same, and therefore, the given differential equation has made exact by this integrating factor. And hence the solution is f of xy is equal to xy cube plus y cube minus y power 4 by 4 plus c star. But f of xy is equal to c dash, which implies xy cube plus y cube minus y power 4 by 4 plus c star is equal to c dash, or y cube of x plus 1 minus y power 4 by 4 is equal to c, where c is equal to c dash minus c star.